Hello students, today I am in front of you to explain one of the practical of your course, which is transfer characteristics of an operational amplifier in inverting and non-inverting mode. Now these practicals would have been going on regularly if COVID wouldn't have been there, but now as with these COVID restrictions, we have decided, at least for the students to get a feel, we will explain the practicals to you over here in front of you, by which you will have some idea as far as what physics practicals are there in your regular course. Correct? So till now I have taught you the mathematical methods in physics, okay, and oscillations, waves and sound, but today I am in front of you for this practical. So basically this transfer characteristics we need to know in both the mode, inverting and non-inverting. So to go further, we will just see what is this op-amp basically is. So this op-amp is basically a 8-pin IC drawn in this fashion. So this is pin number 1, 2, 3 and 4, 5, 6, 7 and 8. So I'll write it this way: 1, 2, 3, 4, 5, 6, 7 and 8. So out of this pin number 1 is for offset null. Okay. Then this is pin number 2 is inverting input. Pin number 3 is non-inverting input. Pin number 4 is VCC. So over here we'll say minus VCC. Pin number 5 is offset null. Pin number 6 is over here for output. Pin number 7 is plus VCC, and this is NC or not connected, or we can say in short dummy. Right? So you have a IC like this. So this is my pin number 2, pin number 3, pin number 2 is inverting, pin number 3 is non-inverting, and pin number 6 is the output. Here I have plus VCC, here I have minus VCC. So minus VCC is pin number 4, plus VCC is pin number 7. Now over here I will draw the pot P1 in between pin number 1 and pin number 5. So this helps for the offset null adjustment, this pot P1. Correct? So this is basically the IC looks like, which is a small 8 pin, basically is found in DIL package. Now what is this DIL stands for? Dual in line package. This is 2 lines. In one side you have pin number 1, 2, 3, 4. Other side you have pin number 5, 6, 7, 8. That's the way usually this IC is found in the market. This is used commercially in many of the books. So before doing the practical, the first thing you have to do is adjust this null. So offset null is the first step which one has to do, and for that the experimental arrangement is this way. So I have my op-amp. This is minus, plus, output. Here I have a feedback resistor, pin number 6. This is 2, 3. So here I will show a resistance and everything connected to ground. This is output. Then here I have plus VCC, this is minus VCC, and this is a pot. So over here, what I have to do, I'll keep this input, this I'll call RF, this is my R1, or I can say RS, whatever. So the first job is take a DMM. DMM has got two probes, one is red in color, other is black in color. So red will be over here, black will be over here at this point. Your job is to adjust this port P1. This is called as a port P1. So everything is grounded, right? All these inputs are grounded, and you are going to adjust this port P1 till you get on your DMM 0 reading. So what is the requirement over here? The DC range is adjusted on your DMM, and DMM should show perfect 0. That's the adjustment of this port. And once it is done, then you do not have to disturb this port at all. This is called as the offset null adjustment for IC 741. Okay. Afterwards, we'll move towards the non-inverting mode first, and then we'll go to the inverting mode. Now for the non-inverting mode, we'll have to again rub this part and start off with the diagram. So for the non-inverting mode, I do first. Non-inverting mode. In this mode, the diagram is like this. This is pin number 6. This is plus. This is RF. Okay. Now over here, this is my non-inverting mode. So definitely I'll have to give input to pin number 3. Correct. This is 3. This is 2. So now I will say that this input is grounded. And occupy little lesser space. Okay. And say this is grounded. And here I will try and show the input. This is the other part. So this is my E. This is also E. And here I have what is called as a switch. This part will go over here. Fine. So this is called as SPDT switch. So this part is negative and this part is positive. Correct. And here this will come back connected over here. Fine. So this is my connection. Obviously I have to show the VCC also. Plus VCC, this is minus VCC, and this is the null zero adjustment. This is my port P. Fine. So this is, I say, my R1, and this is RF. Correct. Everything is done. So one part is plus, this is minus. What is the SPDT stands for? This is called as single pole double throw, which means at a time only one circuit will work. Suppose my switch is towards this, so this part will be in action, and when it is towards negative, this part will be in action. That's what is the meaning of single pole double throw switch. Now over here, to perform the practical, what you need to do, you need to change the input and measure the output. Over here, what is my main job now? My main job, or first the formula I can see. Over here, the theoretical gain formula. What is the theoretical gain of this non-inverting mode? Theoretical gain formula is 1 plus RF divided by R1. RF is chosen to be 10K, correct? And R1 is chosen to be 1K. So I can say 1 plus 10k by 1k will give me 1 plus 10, that is 11. So this is my theoretical gain of this non-inverting mode. Now to take the observation table, what will I do? I'll say V in and V out. So here also this is first part, and in second part I say V in and V out. Correct? So over here the first part will be increase the voltage from 0.1. What did I do now? My switch is towards the positive. So input will be positive. So I say 0.1, 0.2. In the step of 0.1, I'll keep on increasing the voltage till I reach to 2 volts. This is my VI. I have to observe now what is my V out in this case. So in this case, my output will be also positive, and the values will be either 1.1, 1.2, right, 1.5, then 2, random values. And they will keep increasing till my VI, the input voltage, will reach to some proper voltage. Then later on this will become almost stable, and you say by around 1.8, 1.9 and 2, I'll get the voltage around 11.9 or 12, which is my highest voltage for the op-amp 741. This is the first part. In second part, what will I do? In second part, I will change this SPDT switch towards the negative. So in this case, definitely my V in has to be negative. So here I say minus 0.1, minus 0.2, minus 1.8, minus 1.9 and minus 2.0. Right? So in this case, my output expected is also minus. So I will be getting the output like 1 point something, 1.5, like that, till I reach to minus 11.9, minus 11.9, minus 11. So this is the way I will get the input to output table or variation for the non-inverting mode is concerned. Correct? So which means here I will be getting the input positive, input negative, output also negative. So if at all I want to draw this transfer characteristic, what will I do? I will take this way. So on x-axis I have my input volt, and y-axis I have my output voltage. Correct? Now over here, what did I say? First, this is the first quadrant where I'll have the values plus plus, second quadrant minus plus, third quadrant minus minus, fourth quadrant plus minus. So suppose I am increasing the values slowly over here on the x-axis from 0.1, 0.2 like that till around 2 volt. What is going to happen? Even my output will keep on changing and I'll get the values over here. So in the first part, as you increase the output, increase the input, output also will increase, and later it will become saturation at these values. So I can say this is my Vsat positive. Correct? This is the first half. This is my first quadrant. Fine. Now this is concerned is what? This is minus minus. So I'll come over here and my graph will be like this. And later it will become steady. So this is my Vsat minus. Fine. So this is the important point, and over here this is the important point. And this part will give me the range. Correct? These are the values for my input. These are the values for my output. Correct? So I have reached from V saturation plus to V saturation minus when I am changing the input by this SPDT switch from positive to negative. So this is the way my non-inverting terminal is going to give me the output curve. This is called as transfer characteristic of an op-amp in non-inverting mode. Correct? Now exactly opposite will happen as far as the inverting mode is concerned. So now there, what should happen? My input earlier now was over here. Now it will come over here. So it was over here, now it will come over here. That's what the only difference will take place. Rest all, only one thing I forgot, that is it has to be grounded. Even this output has to be grounded. So everything is covered as far as the first half is concerned, which is the transfer characteristics of my non-inverting mode. Now I will move towards the inverting. Now for the inverting mode, what corrections I have to make? I have to make the corrections only to this part. So I will rub this part and do the connections over here. Same way, the output also will be almost similar, only this graph I will have to change. So over here, so in this case, I just try and show it over here. So this is my negative. So I have to show it over here that the input is going directly to this. Okay, and this part is directly grounded. Correct? This is grounded. This is also grounded. Right? So this is my pin number 2. This is pin number 3, and this is my R. Right? So in case of inverting mode, the theoretical gain formula is what? Only RF by R1. There is no 1. So in this case, the value will be only 10 and not 11. Right? So value will be only 10. Correct? So in this case, what is the difference over here? I have given my input through this SPDT switch, single pole double throw, to pin number 2, which is the inverting, and number 3 pin was non-inverting. So when this happens, when I am connected to positive, what should happen? This positive should go to this pin, and later the negative should go to this pin. So first is positive, it means I have to have the VI to be positive. Right? So when VI is positive, output will be negative. Correct? So here I will put only the minus sign. Rest all will be similar. Correct? And when I have given the negative, when I am connecting the SPDT switch to the negative part, what is going to happen? My input will be negative, correct? And in this case, the output will be positive. So I'll have to rub this sign over here because of the inverting word. In this case, what happened? The first it was positive, so input was positive, output was negative. When I switched from SPDT from positive to negative, my input was negative, but output was positive. So in this case, what are my quadrants? Basically, this is plus minus. So plus minus, where I will be? In the 4th quadrant. Right? So my graph will be somewhat in this quadrant. So over here, and then saturation. So this point is very critical as far as this is my V saturation minus. As far as this part is concerned, this is minus plus. So I will be over here in this quadrant, and it will be saturation over here. So this is my V sat positive. Right? So this is my important point. Right? And this is the range which I am getting for my input values. So in short, this is the transfer characteristic what I observed for my inverting mode, where I am getting my VI to be positive, that time output was negative, and when my Vin was negative, output was positive. That's the reason I covered these 2 quadrants over here. In the first, I had 1st and 3rd quadrant, and now I had 2nd and 4th quadrant as far as my inverting mode is concerned. So this is a very, very important practical as far as knowing how to draw a transfer characteristic for my operational amplifier, which is IC741, which is commercially used for many applications. As the name operational amplifier, it is used for doing all the mathematical operations starting from addition, subtraction, multiplication, division, integration, differentiation, and so on and so forth. Correct? So if you have any difficulty in this practical, please message me directly. I will be able to answer your difficulties. Okay? And if you like this video, don't hesitate to like, subscribe and comment on this video. Thank you very much.